Welcome to what I believe is week 4 of the lecture series / course on reproducible research in R, taught partially online and partially at LSU. This lecture will be recorded in parts because I went slightly out of order and then I had some issues connecting to the Zoom cloud server to record it. My internet was a little bit spotty. I'm back up and standing and healing. It's not looking too bad. It's from my small little bike accident. So yeah, let's get going. So last week's lecture was fairly long, and it sought to go over pretty much all of our basics. And my point there was I wanted to teach you sort of the full breadth of programming concepts generally and how they're implemented in R. And so we went over things like conditionals and if statements. We went over for loops, and we went over apply statements. We went over different data structures and types. And then lastly, we ended briefly going over writing functions. And we'll touch on that again today. And so functions are an incredibly useful way to make your code portable to other applications or data sets or use cases. Yeah, especially as you start developing your own projects, you'll notice that you will use really similar functions across different projects. And so things like making a function that can plot the mean and confidence interval of an arbitrary size data frame, right? So if you have like a column or a 2 data frame column, you can write a function that will plot the mean and standard deviation or standard error of those 2 columns, and then you want it to be flexible, and so you can actually write it to where it'll do n columns. And that's a really useful function that you can just sort of package and keep on hand. There's been many people that advocate for actually building your own R package, basically with those functions. And I've started to do some of that, but my functions are pretty general, and most deal with plotting. But eventually they won't. Eventually they'll get a little more specific. So I think it's a really good practice. For people that are enrolled in the course, in the discussion section, we're going to talk about Morwick, Bodiger, and Mullen packaging data analytical work reproducibly using R. And that relates to this sort of general topic that I'm going to go over now. And so it will be less of sort of getting into the weeds in terms of a computational tool and more of high level, how do you structure your data and your code and your manuscripts in terms of just the file structure. And so some people advocate for packaging manuscript and code as an R package if it uses R. I think that's a little bit too software specific. Ideally, it would be something that could handle multiple different sort of like code languages and code streams. So if you're using multiple coding languages for a problem, packaging it as an R package may not be the best solution. Though R does play nicely with some languages, it also really does not play nicely with others. Okay, so I'm going to share my screen with my lecture notes and a terminal window, and we're going to go over how I personally structure how I personally structure my projects. And this is not prescriptive. You can sort of do it however you want it, but it's really nice to be, if it's portable across different projects. And so you don't want like 20 different folders, all with different structure, because that's just a headache. And it does hinder sort of reproducibility as well, sort of inherently. All right, so I'm now sharing the lecture notes, which are also available on the GitHub page. And then I'll open a terminal window and make the text a bit bigger, so hopefully that'll be clearer. All right, so last week we went over pretty much like but now I want to back out and just sort of examine structuring your pipeline to make your research reproducible. I go over in the notes a little bit about the clear benefits to sort of building your quote unquote analytical pipeline, or basically where your code and your manuscript files are located. Is the gist of what the analytical pipeline is. All right, but before we get into how we structure sort of our analytical pipelines, I actually want to go over a little bit from last week and dive into more about flexible function writing as well. And so this is because I don't think we had enough time to really delve into it, although some of it could be repeated, but writing functions is incredibly important in R, as well as in other languages. So I'm sharing my screen on this side, along with the lecture notes. And we've talked briefly about the goal of a sort of analytical pipeline. And one of the sort of components of an analytical pipeline is the analysis itself, the code that will be required, the data that is required to complete an analysis. And so this course is on reproducible research in R, and therefore I'm going to talk largely, if not solely, about R code. And so when you're working in RStudio, you can just write code directly into the console, right? However, it's a little bit clunky, and you may want to reuse code as well, and it's not reproducible if there's no sort of written history of it. So if other people need to have some file that they can use as a recipe to complete the analysis. All right, open up familiar RStudio. That's the lecture from last week. Okay, so we're just gonna, it's just so we have the console. And we'll actually shrink that side, so all that we have is the console. So we went over the general structure of function writing in last week's lecture, and that's you name some object as a function. So you specify, so you normally say, if you were assigning a variable, you'd use the assignment operator, and then you give it some values. Like, for instance, that value, which could be a numeric vector, or this could be a data frame, or something else. However, we want to specify here that we're creating a function. And so you do that by using the assignment operator, but then making sure you specify that you're creating a function. In the parentheses, so function is a function to create a function, if that makes any sense. But within these parentheses, you give it the arguments that you want your function to have. And so, and actually, I'll just copy this over from the left and go line by line. And so then it starts with the curly bracket. And if you ever see this character in R, it means that you haven't completed. You left some open. You left like an open curly bracket, or you left open like a parenthesis, or like you got something hanging that's just not done. And so here we're using that to our advantage, just to run things line by line. And so here I structured this function just as sort of an incredibly general thing that doesn't actually do anything, and then returns something like that also doesn't exist. So maybe we should specify that ret equals something. And so the idea is that in here it does some stuff. There I'm writing doing stuff as an inline comment. So it's really useful to comment your code so that you know exactly what's going on. Because there are some points when your code can get very confusing. Like Ideally, you're writing code for someone to be able to read it, so you're writing human readable code. But I mean, the most important thing is that code is efficient and machine readable. And so, arguably, most important. There are many that like sort of wouldn't agree with that. But in terms of like, I would rather have my code be less human readable and more robust to errors and efficient. There is like a definite trade-off there a lot of times. That's the small aside. So basically, make sure that you document your code in line using the hashtag or the ampersand, not ampersand, the pound sign, or hashtag if you're too young. I don't know. So then we assign the function ret as NA, and then we have this, which we haven't seen before, and that's that you return the object. And so the function does something, it makes something given some form of arguments, and then it has to hand it back to the global environment. So basically, like, within a function, a ton of stuff can be created, right? So we created this one object called a ret. And then we need to return ret once we calculate it. And then we end the function with the curly braces. And then we go back and we're cool. We have control of our console, no more of those little plus characters or plus symbols. And so now we have a function where we can specify some arguments, call it arguments, and they're not used, so it doesn't matter what you hand it. So I'm going to say arguments equals 1. Okay? And this should hand us an NA value. And it does. And it makes this ret right here and returns it. But we notice that in our global workspace, ret is not there. It's an important distinction that I'm sure many of you know, but I'm just throwing it out there because it has some kind of cool implications. So basically, anything within a function is assigned in that tiny little localized environment and not in the global workspace. So you always have to return anything that you want to get out of a function from the function. This is really useful when you do a lot of manipulations of large data and you don't want to return something that could take up a lot of memory. So that does it within the function, and then it processes it through, and maybe just returns like 1 or 2 values instead of those intermediate data products, which can get really large, and R has to hold everything in memory, and so like all the objects are held in memory. So that can start to stretch the limits of your computer potentially. All right, and so we talked a little bit about inline documentation, which is that in your function, it's just saying doing stuff, which is not great documentation. You want to be a little more specific than that. But here, I could say we're setting a value to NA that we're going to return, which is not much more specific than doing stuff. But there are other forms of sort of documentation. There's inline documentation, and then there's actually documenting the overall function, sort of in like a meta way, right? So we can document each line of the function, but we can also document the function itself. And we went over that a bit last time. I don't think we went over the DevTools command on how to actually document the function. And so DevTools is a really useful package that can sometimes be annoying to download, but it's not too bad. It has a lot of dependencies. But it's a really fantastic package for documenting function. It has a ton of things, releasing packages, building packages. It's fantastic. To run documentation. And we went over that briefly last time in terms of how to structure your documentation. And so you can write documentation within the same R code block that you write your functions, which is different than how it used to be. So when I was first learning R, you had to basically create your own manual files when you wanted to just develop an R package, which was kind of annoying. There's sort of, yeah, I think it was LaTeX structured, but still, like, it's much better to see how you structure your function and then be able to write it right alongside that function. So when you say like param x and you give a value and say lx is a number, what if I change it to like be in a different order or something like that, and like I have to always have the manual file open and the code open? It's kind of a pain. But here now it's lovely. And so we use the # followed by the apostrophe to initiate the sort of documentation environment, and then we use these ampersands and arguments to those to specify model return. So this, maybe we should say the sum of x and y, because that is what it's going to return, a single value. But it's, yeah, it's actually flexible enough to work with vectors as well, or some matrices if they're the same size. There's also a place for examples, as well as this command, which you won't need to know if you're not developing a package. But if we were for examples, we can list something like add x, y, 5, and 10, and that should produce 15. And so once we get, and then we get down to the body of the function, and we see we have this function that we created called add x, y. And then we use the assignment operator, call it a function, and give it 2 arguments, x and y. And then we take the sum of the concatenated vector of x and y. So it actually may not work with matrices. I don't know if that would just mash their formatting or not. It probably would work. Okay, and so this, this implicitly returns the sum of x and y. Right? So before we wrote a return command, we said return that. And that isn't the better way to do it, but you can also just simply have something that would output and print to screen, like just saying, calling the sum. And we can run it either way. So in the RStudio workspace to the left is the old function. It runs and it outputs. And then we can load the new version of the function, run it, and it outputs the same thing. And then, of course, we can sort of assign the things that a function returns to a variable. And so let's say we want to assign variable a to add that vector and this vector. And the way we wrote the function, it ignores things vector size. So it's just going to take the sum of this entire thing. And now it doesn't return anything because it stored it within a, and a equals 43. All right. So this is good. Like now I think we more thoroughly discussed function writing, or maybe just rehash some of the things we previously went over. But now I'm going to sort of go into some characteristics of not so great functions and how we can potentially just make them better. And yeah, like rules of practice, rules of thumb when you sort of want to write functions that can especially be translated across projects. The first one is avoid hard coding. Hard coding means if you have a, let's make a matrix, we'll call it mat. Yeah, this will be useful for this example too. And we'll give it 1,000 values from a uniform distribution, and we'll give it n-col 10. So it means it has 10 columns, 1,000 random draws occupy these 10 columns, and it's a matrix. So we have a 100 row, 10 column matrix of random uniform draws. So bounded between 0 and 1. Yeah, and so let's say we wanted for our analysis to get the mean of this first column, or we may want to write write a function that says get column mean and then indexes a certain column. So let's say the first two columns of my matrix are like site information or like some other variable that I don't care about. What I really want is just to get the mean of the third column. I can do that. I can specify the mean of the third column of the input matrix. And maybe I have a lot of matrices that are structured where I would want to pull out the third column. However, that's just bad practice, because if I had something where I didn't want to take the third column, all of a sudden that function is useless. And so we want to write something that's general that avoids hard coding. Hard coding being specifying that 3, saying take the third column. Instead, what you can do is right here where I say I redefine the function get column mean, and now I hand it an additional argument called index. And we can even set index. So let's say we're always taking the third column of get the mean. We can set a default value for index such that this function is still usable. Now it can flexibly index columns. And so by using this index called index, we can take the mean of any column. And that is useful. And now we'll go into a little bit of error handling. And so our function here, we now have index. So it's building on each other. And so a good function should handle potential errors and error out gracefully. And so if it's going to throw an error, you want it to be informative and tell the user something. It's like, oh, that makes sense, why this function won't work. And so let's say that one of the values, and let's use the third column just for fun. Let's say that value 10 of in the third column and the 10th row of this matrix called mat, we have an NA value. That's what I just sort of coded up in there. And now when you try to take the mean of that, so we'll load in that function and we'll say get column mean mat. And the index is already defaults to 3, so we don't need to say it. And it spits out NA. That's not ideal, because a user could be like, oh, that's weird. Why is it spitting out NA? And so how you can do that is using conditionals. It's called error handling. So try to make your function such that it can be handed garbage and call it garbage. And so here, we don't inherently just remove the NA value because maybe that's not what the user wants. What we do is we say if, and then hopefully the syntax looks familiar, if any of the values within this column are NA, so if any is NA of this matrix column that's indexed using the index argument, then issue this warning. Tell the user what you're going to do with the data. And the user could be you or it could be somebody else, but tell the user what you're going to do. So this issues a text warning to the screen that says, there's some NA values, I'm going to ignore them. And then what it does right here is takes the mean and NA omits that. And so we can run that. Okay, and then we can run that on index 3, and it gives us an informative warning message that we provided, but also gives us what we sort of want, which is that mean value, ignoring NAs. I think this is the last main hint, or not really hint, last main way to write good functions, and that's make them flexible. Flexible enough to solve their purpose. Let me stop itching. It's my cat. And so now we're building on this function again where we have get column mean, and it now ignores NAs. But just taking the mean of a column is kind of restrictive. And so let's say you're in a situation where you want to do some plotting, or you want to calculate not only mean, but standard deviation or standard error or something like that. You can keep the same function and use it across multiple different, you can apply other functions within that, if that makes any sense. And if it doesn't, I'm going to go over it now. So this one's called get column mean. I called it bad, but it's not bad, it's fine. But here I incorporate that flexibility. And how I do that is now we have a new argument, which is called func. And it defaults to take a mean. But you can hand it any function that'll operate on numeric data, right? And so it's going to say any, it's going to ignore NA values. And then here it's going to apply that func, which takes the value of mean by default to that numeric column. And so we can say get column info mat3, oh, sorry, so mat index equals 3. That's our mean, that's the default value. Why are we getting a different value than we did before?
2 hours later.
Oh, I see. Am I still recording? Yeah, it's still on. I see. So before we didn't set the actual index because we didn't default the index. So that was my fault. We can go back and I'll make sure I add in all the defaults for the index. So it was actually taking the mean of the entire matrix. Because I didn't specify before to get that value. See? So that was just me being silly. All right. So now we have this function called get column info. And we can apply that to mat. We can say index 3, and then we can, the func mean, we don't have to type. Both of these are default to 3 and mean by the default. That gives us that, but now we can also apply other things. That's the standard deviation, that's the median, that's the min. Yeah, and so I talked about plotting a little bit, or just now in that one sentence. And we'll go over how to plot and visualize data in a future lecture, but these functions that you can make as flexible as possible are incredibly useful for plotting. That's, I think, I have an R package that has functions just that I use across projects. It's helpful to have. And I think like 70% of them deal with plotting in some capacity. And so super duper useful. So here I basically just make a function. We won't even go over this. We'll go over the plot function and the par functions and other visualization functions in much more detail in a later lecture. So I'll skip over that for now. So now I would like to shift to talking about how to actually structure your repository containing your information, like your analysis files, as well as your manuscript files, etc. And so I will go back to screen share mode, and this is, again, just how I go about structuring my project repositories. It's not meant to be prescriptive. So yeah. There are two main folders in the project. So here on the left in the terminal, I am, actually we said we're going to use the terminal through RStudio, didn't we? I feel like I remember saying that. I'm going to open up RStudio and we'll just use the terminal through RStudio. So we click over from console to there. Okay. And we want to change to the documents folder. We want to change into new project. And now we have how I structure my repos. So this is uniform across the majority, if not all, of the projects that I have worked on. And so highlighted with green background are folders, and then the ones just in green text are just files. And so, and this is actually missing a couple of files. So this is actually an old template that I used in the past. And so we can make them. We can make the files. The first of which, according to the lecture notes, is a Readme file. And that is present, so that's good. So this is a markdown extension file right here that contains information on the project itself. And this one's probably really skeletal. Yeah, it actually contains nothing. So cat is a way to output the results or the contents of a file to the bash command line. But your README file should not be empty. It should actually contain a bunch of information. First and foremost, about you as a developer. So what's the story with the repo? If it's on GitHub, it'll be associated with your username, but you still want to provide information, not just on your name, but on any of the developers or collaborators that are working with you on that project. And so this is the name. I also name my projects, which I think is useful. And so GitHub repos tend to, and it's just like sort of fairly good practice to not include spaces in the name and to use some sort of familiar case strategy or typeface. I don't know what word I'm looking for is. So basically, I use lower camel case. Typically, almost always, not in this case. This is an old project template, which is you capitalize the first letter of every new word. You don't include spaces, and the first consonant is not, or the first letter, sorry, consonant is not capitalized. But here it is, so ignore that. Your README file should also contain information on the background or motivating question of what is it and why should I care? It warned me my internet connection is unstable, so hopefully this is coming through. The third thing that should be in your README file are other libraries or prerequisite information before you can run. So things like what version of this, what version of that, how to download the package, how to make sure all that, if it's a package, how to download other associated packages, and make sure all the dependencies are met. That's important. And that's not even super duper necessary to be in the README, but it better be in your analysis folder. Otherwise, your analysis is sort of fundamentally potentially non-reproducible. And that's the point of this course. And so these two sort of go together. How do you work with whatever product you're giving the person or distributing among people? And so installation and dependency issues are important. If you're developing openly, then somebody might post an issue and say, hey, have you considered changing this to this? Or they may have contributed in some way. You should list them in their README file and give them credit for the work they're doing, as well as acknowledging potential financial sources. You'll also probably do this in the manuscript, I would hope, but that's always nice to be upfront with that. And this is an exhaustive list. You don't necessarily need to incorporate all of these things. I sort of tend to not, I write that comprehensive of README files, but they are important and contain a lot of important information. README file should also contain, related to sort of contributing, a code of conduct, ideally. And so that's just a statement of basically what you'll accept, like what is laying out behavior of potential developers. And so you just want to put something that says like, don't be not a good person when you help develop this project. And so, yeah, it's set in both in terms of standards, like, yeah, we should use inclusive language, we should do this and that, and also just clearly outlining things that are immediately unacceptable. That will just get you boom, banned, like kicked off. And that's sexualized language, just mean-spirited people, yeah, and then incorporation of sort of politics or things that would go against or cause a lot of potential controversy. Lastly, what's going in your, and some people have code of conduct as a separate file, some people don't have one at all. Our OpenSci, a great developer collective, has a pretty standard one, and then I think they also include it in each package that they have. So they have one for the whole sort of enterprise or organization, and then one for each package. I believe, I could be mistaken. And lastly, what you want in that README is a little bit of information on the license info. And so when you release something, if you release it openly, you need to tell users what they can do with it. And so I think, what is the default license? I want to say it's MIT. There's a bunch of different licenses, and you can pick from them on GitHub. And I can show you that really quick, because I just have GitHub open. I just need to drag it over. All right. Let's go like a random, I don't know what repo I want to go on. What's Scott doing? So yeah, and this is a good example of how to structure a repo as well. And so we can zoom in on this and see what this developer is doing. And so they have a folder called scripts. They have something in command. They have the actual package itself, which I'm not sure what this is meant to do, but we can go down here and then see that this is their README file. And it contains a clear title, contains all of these badges that cover things like code coverage, documentation. So that's code coverage, meaning what percentage of their code is properly documented, as well as a build. And so this is in Travis, which we'll go over, I think, in this lecture. And then this is perfect. It gives a clear, concise statement of what the product is. PDF CPU is a PDF processing library written in Go, supporting encryption. Perfect. Motivation statement. Focus. It gives all the info commands. It gives information on docs. This is lovely. Even a demo, so installation, which we talked about, that should be there. Contributing. Yeah, nice. So how you will contribute and what he wants to see in terms of contributions. So bug fixes, feature requests, like, yeah, cool. A list of contributors, a code of conduct. Man, this guy's killing. This is perfect. This is a good example. This is a well-written README. Yeah, so he links to a code of conduct. That's a separate file, but he also links to it here. And then here's information on license. And so this is a license under Apache 2.0. Other licenses are, and then he has a license file. And so the license file is all the legalese that goes into who can use your product. And so Apache is semi-common, but not that common. And then the more common ones would be the MIT license and then some of the Creative Commons licenses. And I think I go into a little bit about Creative Commons. And so Creative Commons is an organization that is developed around providing a nice gradient of licensure such that people's work could be preserved and respected. And you can place some stipulations on it, or you can go and make it completely open and usable by everybody. And so if you just have sort of the CC1 or the sense of Creative Commons, or just the CC0, it means that it's entirely open source and freely available for anybody to use, to reuse, to use for commercial products, to not say where you got it, just like, here's my product, do with whatever you want. Do whatever you want. And then there's different additions that you can toss on top of cc0. The first one that I'll go over here is by, which means by attribution. So it's open and freely available to use, but you have to attribute. You have to say where you got it from. You have to cite me, essentially, as the original creator of some product that you're using. SA is a second sort of stipulation or add-on, which means share alike. It means that if you utilize my code or something with this license, this share alike license, your work also has to be licensed in Creative Commons and licensed with that share alike addendum or add-on. Some people call it a quote unquote parasitic license, but I think it's kind of a positive thing. The next one is sort of the ND, standing for no derivatives. This is an interesting one. It means that you can use the code freely, but you can't modify it. And so that you can't sort of build on it or change things. It's rare that you see the no derivatives flag really used, and so more you see it in sort of niche cases. Like I give an example of an internet security company or something like that, where they want the existing code base to be available, but they don't want people to make spin-offs of it and sort of corrupt the code base, but fundamentally change or modify the code base. And then the last one is the NC flag, which stands for non-commercial, which means that you can use the code or data product or whatever it is that's licensed freely, but you can't use it for commercial profit. So that's kind of cool. All right. So other things that are in a structured repository. We haven't gotten into folders yet. We were still on the top level. We got our make file, which I do go over later. We need a git ignore file, and so we can add that using touch. And the git ignore file basically just tells Git, or it tells your local machine which files to version, or more specifically, which files not to version. Oops. And so let's just open this up in gedit, which is the text editor that I'm using on the right. It's empty. And let's say we want to ignore, I don't know, is there anything in the analysis folder? Just one code. We want to ignore the code file, which we never would, no, we don't want to do that. Let's say we're going to make a data file, and it's going to be called data, and it's going to have an rdata extension. We put that into a separate, or we put that into the git ignore file, and now Git doesn't version that. The reason why you'd want to do this is if you had sensitive information. So what if data.rdata contained information that you couldn't distribute widely due to different sort of stipulations of government or IRB or something like that. So you want to put it there and make sure that flag was correct, that path was correct. Yeah. Also, GitHub only accepts files that are less than 100 megabytes. So if you have big files, even if they're like big data files, even if you can share them, you may not be able to when versioning on Git due to that file size cap. All right, and so now we're getting into the actual folders. And I'm actually going to not get into the folders because I want to go over that. Let's go to the top level of the repo first. So the only other thing that's a file that exists on the top level, I believe, is your make file. So I'm going to scroll down and we'll see. And I think the reason why I moved it down there is because when I typically do a make file, when I typically write a make file, it actually sort of just lives in the manuscript folder. So I'm actually curious as to what this make file even looks like. Issued, this is hard. Oh, I see. That are issued. I'm going to clear that. I'm going to open the make file in a text editor in gedit next to it. All right. So make files are basically a set of shell commands that are in a bit flexible way. And so I'll say it by example. And so we're going to go now into the manuscript folder just to give you a brief overview of how that looks. Okay, so how I write manuscripts is I have, and this is a second Makefile, which should be the same as this over here, as this text over here. And so we have manuscript.txt, and that is a LaTeX file that needs to be compiled to PDF. So there's many actions that a Makefile can do, right? And so they're all going to start with the same thing. It's going to start make. Okay, and then here, if we type in make paper, it should run all of these shell commands. And those shell commands will compile the manuscript, those 4 commands, and then remove all these extraneous files that don't need to be there. There's also make view, which will open up the PDF of the compiled manuscript using events, which not everyone has. So this is actually like kind of a poorly written Makefile, because I'm the only one who uses it, so I'm sorry. And then there's just make clean, which will just remove a bunch of stuff, including the rendered PDF or any PDF that's present in that repository. And so we can try that out, say make clean, and we see those commands are issued. It doesn't have any effect. So let's try to build the paper. So we say, let's say make paper. And there it is, it's running all of the LaTeX commands and doing all the stuff, and then finally removing some of those junk files, all those junk files. And so now what we have that we didn't have before is the actual PDF manuscript. So let's say we want to see it. We can use that make again and say make view. And here it pops up. Man, this is a really old template. This is back when I was doing my PhD. So this is my template from when I was in the shoes of the people that I'm now teaching at LSU. This is my workflow when I was then. And you can see that I cite myself from 2014, and then it has all the structure of a normal manuscript written in the tab. All right, well, waiting for that little bar to go away, and then we can close that. All right, so we're already in the manuscript folder, so I can also show you around there, and I did very briefly. We'll go over LaTeX in the future, maybe, if people are interested. Currently, I have it, as we'll go over it a bit. But this is sort of where my manuscript lives, and it has subfolders that are empty, such as the figures subfolder and the supplement subfolder. Okay, the supplement does have a supplement.txt file and its own make file. And the make file will act on the supplement.txt file, but also probably have these same commands as well. So now we're going to back out of that and go again to the high level. Yeah, I think that was all I wanted to talk about in terms of the manuscript folder. So we also want to check out the analysis folder, which in this situation just has one file, which is an RMD file, an R Markdown file called Dallas code. I think it's also important to make sure you keep your data in a data folder, typically nested within the analysis folder, but it's up to you where you want to put that. Just a place that's easy sort of to read from, because your Dallas R code will be reading data from there. So that's at the top of that Dallas code.rmd file looks like. So it has my YAML markdown, or my YAML markup header, and then the rest in R Markdown, where I call in these two packages immediately. And then I harp on the relative path again. And this is a new function that you actually haven't seen yet, because I taught R, the introduction to R, not reading in external data, but just generating data. But how you actually would go in reading in data into R, which is important, is you would say read.csv and then hand it a relative path rather than an absolute path like that. So that's an absolute path, as we've gone over. And then how you'd actively write data is you can use, if I entered R You could use write.csv and then hand it whatever data frame you wanted. And then you say file equals, and then you give it a name, and you say my data.csv. You can also save entire R workspaces using save, and then you just give it a list of things. So let's say like we give it a data frame, and we give it some object A, and then we store it in a file, my data.rdata. So that's just R's own little proprietary data format. If you want to save everything in the workspace, it is even easier, and it's just save image, and then you name the image. And that saves everything that's in the global workspace or the global environment. All right. We talked about the manuscript folder a bit without going into too much detail. The upper level make file, I think this is going to be too much detail, so I'm actually only going to go over it really briefly. But basically, I sort of want to communicate that make files are really important and can be used at multiple levels. And so here, the make file is at the top level. It both renders the analysis code. So the cat's scratching her face again. It both renders the analysis code and the manuscript. And so we can see that by opening it up in gedit. And we see on the right, it looks fairly similar to the other one in terms of the paper. And so that's what it's doing, is that should actually be, yeah, that should be indented. That shouldn't have run. And then it calls relative paths and identifies these as things to work on. In fact, they have a name, but I don't know what it is. And then, so if you say make analysis, it'll do, it should also be like that, shouldn't it? Maybe not. I know it is sensitive to spacing. And so this will run an rscript command that'll run through and render that R markdown file to PDF, and it will call it analysis.pdf. Excuse me. All right, and then lastly, I want to say there's tons of other ways that you can go about structuring your analytical pipeline, and I provide a couple of links for different sort of workflows. The last thing that I want to go over in sort of a high-level way is continuous integration. All right, and welcome back to the last little bit of this lecture, and we'll go over a little bit on continuous integration. So I waffled on how much to actually go into this. Because it gets a little bit in the weeds on things. But I think understanding it conceptually is important, as well as the understanding it well enough to potentially use it is important. So potentially use it, maybe not in practice. So you may not realize it, but the assignments that I give to you are auto-graded using Travis. So I'm using auto-graded using continuous integration. And the service that I'm using to do that continuous integration is called Travis CI. And so now I'll switch over to share screen and show you just a little bit about how that works and how that integrates with GitHub and how it looks generally. And so this may look fairly familiar. This is the R intro assignment in the Bio 4800 organization. And so if you don't have the link, there it is. I'll also try to make sure that the link is available in the description of this video and of previous videos, hopefully. And so you see this repo that is the R introductory assignment that you've hopefully completed by now, maybe. You can see it has information just like the sort of analytical pipeline information that we had there. So we have a gitignore file, and then we have the main file, which is the actual assignment itself. We have a readme that includes information on files and your name and things like that. Doesn't include a code of conduct because you're the only one who's going to be working on this, right? It's a private repository, so it's not meant for public consumption, basically. And one thing that I want to point out is it has all this in this file called .travis.yaml. And so there's many ways this file could be structured. This is a file that's YAML, so it's yet another markup language, the same thing that lives atop of your of the R Markdown code. So similar in structure, but a little bit different. And it basically tells a server what to do with your code once it gets it. And how it gets it is every time you push to a GitHub repository, it updates, and that Travis file says, okay, rerun whatever you want to do. And so very recently, this is sort of a related point. Very recently, GitHub has developed its own sort of continuous integration light feature called GitHub Actions. And so that's worth checking out. I'm not going to go into it now. If there is a demand for it in the class, I'm more than happy to go over what you can do with GitHub Actions as well. And so basically this .travis file, which I can show you now, it is very simple, which is nice. Tells the server how to run the code. And so I tell it the language that I'm writing in. I say it's an R. I tell it the OS that I want to, so the operating system that I want it to be run under. So I'm just running it under a Linux operating system. I could also, I think it has native support for Mac OS, but it doesn't have it for Windows. You have to use like AppVeyor or another service for that. But I'm not too concerned about that. It's sort of simply R code. It's grading an assignment. I don't need it to run on multiple different operating systems, is my thought right now. If I use a lot of dependencies and pulled in from different languages when I start doing like spatial stuff or stuff that relies on C++ in the background through RCPP, then I'd be like, I should probably run on more than one operating system. And then the distribution is Xenial, which is a version of Ubuntu. I think it may be, I don't know, 16, 18, I don't know. What is Xenial? I can Google it really fast. I can type it right. 1604 was Xenial Xeris. Yeah. And then it's telling me that, or I'm telling it to run 3 different versions of the code. One on the old release of R, one on the current release of R, and then one on the development release of R. So basically, I want to test your code to make sure that it'll run on multiple R instances or types or versions, basically. I'm not installing anything. I don't even think that is necessary for me to say skip. And then what I'm doing is I'm sourcing an R file. So I'm saying I'm giving it a bash command that is that to run this big list of tests that I that I use. And now we can look on the Travis side and see what's going on. And so this is travisci.com. It says my build is passing of this template. And so it completed and passed all of its tests. I may change this because I really don't want it to pass the test. I kind of want it to fail the tests. But the way it's written, it's like, yeah, it passes the test, which I actually am still confused on. And you see each one of these jobs are old. Linux when I Ubuntu Xenial. Is being unstable, so I'm just going to stand here and hopefully it'll start working. And so what you see whenever you push code to this repository is it first starts developing the operating system around like getting ready for the worker. So it downloads R. It sets up, here we go. It sets up all these different things about the system, gives information on the server, all of a sudden it does all the different packages and versions. It's got like OpenSSL version, blah, blah, blah. It installs R, and then it clones my repository that I want it to run. Ooh, let me click on that. And then it opens R basically, and then runs through the code. And so this is getting all the dependencies for test that. And it's going to blah, blah, downloading dependencies, blah, blah. So basically this is like what would be run on it's a completely remote machine. And then we're going to get down to it actually running tests eventually. It's installing a lot of packages. Okay, and then we get to tests, which is nice. And so this is where it actually runs that R script and it runs the unit tests that grade your assignment. And so here it's actually passing one of the tests and failing 3. I don't even know how it's passing one of the tests. I didn't write the test stringent enough. This is fail because this is just the base assignment. And then here it's per question, it's showing you how many tests you passed and how many tests you failed, which is super useful. And it gives you a sort of high-level idea about what Travis is doing. Travis is also really useful for maintaining and looking at how, actually, you know, that's a good example. Maintaining R packages. And so here, I'm going to look at branches. And so the master of this branch on GitHub is passing. And it's been running. It runs every so often and builds, and it shows. All right, so this one ran 7 months ago. So I haven't really been developing that much on this one, on this package. And it passed. But you can also see areas where it failed. That's really useful information. And then we can see on pull requests. So these are things where somebody has added. So in this case, this user has added information that they think adds functionality to the package as it stands. And what's really nice is that I don't have to just like read through all the code and try to figure out if everything's working or not. Travis CI runs the unit tests that I've written for the package and says yes or no. Did everything pass? Is everything cool on whatever architecture I sort of tell it to use? And here we see, no, it's not cool. It does not pass. And then you can see the check logs and you can actually understand why it failed or why it passed. So that's another incredibly useful thing about continuous integration. And we can see entire organizations on there as well as whatever. What do I have on here? I don't think I have much. I can go to my dashboard. Yeah, so I have an old package that really old, so it was like 3 years ago, that I wrote to interface with Spotify so I can change songs from the command line and get information on artists, and it's now defunct. I don't think it's useful anymore, although it's still passing, but it ran 3 years ago. And then Metacom and Helmet.R, which are the 2 packages that I actively maintain. So yeah, that is basically it. We can also see the config file for it's and see that it's slightly different. So there's a lot you can do in terms of flexibility with your YAML config file. So this should look vaguely familiar from the other one. So I still say language R. This is other information you don't know about, and then this is for code coverage to get at that percentage of the package functionality that is documented. And then it gives things like notifications, and it natively just builds the package. And so if you handed a Travis .yaml file, you could basically just need to say like that first line or 3 lines, and it knows to run R command check or R command build on your package to get at that. Does your package install on whatever architecture you told it to, which is really, really useful. So hopefully that didn't get us too in the weeds on continuous integration. I will go over continuous integration in class in a little bit more detail because I think it is useful. And that's one of the sort of things that you're going to work into your final projects, people that are taking the class for credit, that I would sort of like to see you do, because it really integrates unit testing and automation really nicely. So it basically does the tests for you, and it allows you to switch over to different architectures in terms of different flavor, or like different versions of R, as well as different OSs, which is really central to understanding and making reproducible code and seeing if your code is reproducible. So with that, I will close this down, stop sharing my screen, and bid you farewell. So this will have been a little bit of a piecemeal lecture, but hopefully it worked out in the end and it is comprehensible. Thank you. Take care.